Okay, hi everyone. So in this video, we're going to be discussing some consequences and results of metric spaces being isometric. So metric spaces and isometries. So first, let's just recall what is an isometry. Okay, so we have two metric spaces. So we say a function f between two metric spaces is an isometry if, so for any 2 points, so let's say x and x prime in x, we have that the distance of these 2 points with respect to the metric in x is equal to the distance with respect to the metric in y of the corresponding images of these 2 points. So the image of f of x is f of x, and the image of x prime is f of x prime. Okay, so this is what an isometry is. The way we could visualize this is x, and this is a metric space y. And if we have a function f between them, if this function is an isometry, then for any 2 points in x, so this one and this one, the distance between them, right? So let's say this is the distance between them. Let's say it's d. Let me not use d. Let me use like L something. Okay, let's say the distance between them is, let's say, L. Then the image of them, so if we apply f to x, we get this point here. This is f of x. And if we apply f to x prime, we get this point here. So it may move the points around. That's okay. But the distance between the image, these 2 points, should also be equal to L. So that's the idea of an isometry. Okay. So what we're going to do is we're going to prove that isometries have certain properties, and that is, the first one is that they are uniformly continuous and therefore continuous. That if you have an isometry, then they are also injective functions, so they are one-to-one. So maybe I should say here what f is. F isometry. And that, so the third one is that the metric spaces x and f of x. So f of x is a subset, of course, of y. So we could view f of x as, well, this is just a range. Okay, that's just the range of the function f. We could view that as a subspace, a metric subspace of y. And x and it's the range of f are isometric. Okay, so let's see if we can prove these things. So the first one is that I want to show f is uniformly continuous. So all of these proofs actually are very straightforward, and they follow pretty much from the definition of what it is you're trying to prove. So for example, if I want to prove any function is uniformly continuous, what does that mean? So that means for any epsilon, so I could say let epsilon be bigger than 0. Let epsilon be bigger than 0, then we could take, maybe let's just say let epsilon be bigger than 0 and choose delta equal to epsilon. in this case. Then for any 2 points in X, so let's call them X and X prime, okay? For any 2 points in X such that, so now I'm just writing the definition of uniform continuity. Uniform continuity means if you take any 2 points in the domain such that the distance between these 2 points, okay, and we're in X, so we're using the distance in X, so the X metric, the metric in X. If this distance is less than delta, then I need to show that the corresponding distance of the image of it, of f of x and f of x prime, I need to show that this is somehow less than epsilon, okay? But I know f is an isometry, okay? So if f is an isometry, the distance of the image of these points in y is the same as the distance of the original points in x, right? That's just the definition of the isometry. But this distance of between x and x prime we saw was less than delta. And I chose delta to be equal to epsilon. Okay, so that's the proof right there. So therefore, f is uniformly continuous on x. And of course, we know that uniformly continuous means it's continuous. So f is uniformly, actually we don't say on x, we just say uniformly continuous because it's understood it's everywhere on the domain. Therefore, f is uniformly continuous, which implies that f is a continuous function on all of x. Okay, so that's the first part of this proof. So very straightforward, that first part. So isometries are uniformly continuous and hence continuous. So maybe I should state what I used here. Okay, so this part here was since f is an isometry. Okay, that's what that was the link between these two. That's why I could put equal there. Okay, so that's the first one. So let's move on to the second one. I want to show if f is an isometry, then f is injective. Okay, or one-to-one. So we can, so the usual way to show injective is we suppose f of x equal f of y, and then we show x equals to y. Another way we could show it, so let me just write down. So to show injective, we could either do suppose f of x equal f of y, and then we need to show this implies x equal to y, or the contrapositive of this, we could either show if 2 points are distinct, this implies that their image is also distinct. Okay, so I just took the contrapositive of the line above it. In fact, it is this contrapositive. This is actually the definition of injective, but the one we usually prove, which is written in the first line, is actually the contrapositive of the definition. So this is usually the definition of injective. And what we actually prove is the contrapositive of it. But anyway, they are equivalent to each other, so it doesn't matter. You could actually use any one of these to show that isometry is injective. So let's try to do it using the second one. Okay, so let's say suppose um, so I don't want to use y because the metric space it goes from x to y. So maybe I shouldn't have used the letter y here, right? Maybe let's stick to x and x prime. Okay, x and x prime. Yeah. So because I want to emphasize that the x's belong to the metric space x, and if I write the letter y, that belongs to the metric space y, right? Because if I just put x and y, you might get confused and think that that element y belongs to y, when in reality it belongs to x. Okay, so let's just keep it x and x prime. So suppose x is not equal to x prime, then, so remember the metric has a certain property where um, the distance between any 2 points is equal to 0 if and only if these 2 points are the same. But I'm supposing these 2 points are different. Therefore, the distance in x between these 2 points should be non-zero. Okay, or if you want to, you could say the distance between them. Of course, if it's not zero and the metric is never negative, then we could write it as the distance is strictly positive. Okay, and that's because these 2 points are distinct. So that's a property of any metric. Um, yeah, but we know f is an isometry, so that means that the distance of the image of these points, f of x and f of x prime in y, right? F is an isometry, so these two things are equal. So this guy is equal to this one, and I know that this guy is not equal to 0. So that means that the distance between the image, right? You don't have to write out all these steps, but I'm just writing out every single step so it's clear. So this means that the distance between the images in y is not equal to 0. In other words, these 2 points, f of x and f of x prime, are not the same. Okay, and that's what I wanted to prove for injective. Okay, so again, for injective, we suppose that these 2 points are different, and we show that the image is different. Okay, so therefore, the isometry F is injective. And the third one is I want to show that the metric spaces X and f of x viewed as a subspace of Y are isometric. So we just need to recall what it means for two spaces to be isometric. So we say that two metric spaces, so maybe here I to recall. Two metric spaces, let's use X and Z, are isometric if there is a bijective isometry between them. If there exists a bijective isometry between them. Okay, so it's just an isometry that's bijective. That means these two metric spaces are isometric. So I'm assuming that F, so suppose Okay, so suppose f from x into y is an isometry, right? So we just showed by part two that every isometry is injective. Then by part two, f is injective, right? So I just need for f to be surjective or onto. Now you see the problem is that this isometry f from x to y, yes, it's injective, but it may not hit everything in y. The range of f, which is f of x, might be a proper subset of y. So all we have to do now is define a, a new function that goes from x into f of x. Okay, I guess, yeah. So let's see if I could come up with a bijection between x and f of x. I'm going to let a function, let's call him g, go from x, and instead of it going into all of y, you see the original problem was that y may have been too big. The range may have been too big. So let me restrict the range down to this set, f of x, which is the range of f. Okay, so I'm going to define a new function, g, going from x into f of x, which of course you know is a subset of y, defined by g is just equal to f, okay, for all x and x. In other words, this is just a fancy way of saying that the function g is the same as the function f. All I am doing is just changing the codomain. So the codomain may have been too big, so I'm setting the codomain now to be the exact range of the original function f. Then, by construction, g is surjective. Right? G is surjective, and since g is equal to f, it's also injective. Right? Remember, we said f was injective. So surjective and injective means bijective. And remember, the original function f was an isometry, and g is just equal to f. It's the same function. You're not the only thing you're changing is the codomain, but it's the same function, which means that this new function g will also be an isometry. So it's surjective, injective, and an isometry, right? And that's the function you need. Therefore, so what do we have? We have a bijective isometry between x and f of x. So therefore, x is isometric to fx, f of x, right? Maybe I should specify here exactly what this thing is. So note, right, that this that fx is just the range of f. This is the range of f. If you want to, it's the set of all points in y such that, oops, this is set of all f of x and y. The set of all f of x and y, where x belongs to x. Okay, so it's just a set of all function value, the usual range of a function that we know. So note that the range of f is a subspace, metric subspace of y. Right, and we already spoke about if you have a metric space and a subset in it, how you could convert that subset into a metric subspace. You just put the same metric on. Okay, so that's the true results Okay, that we wanted to prove here. Okay, so in this next result that we want to show, um, previously we looked at some properties of a map that is an isometry. Now we want to look at properties of metric spaces that are isometric. So if we have two metric spaces, x and y, metric spaces, and a function between them that happens to be a bijective isometry. So in other words, the metric space x and y are isometric. So what this result is essentially going to show is that when you have two metric spaces that are isometric, their metric sort of properties, so properties involving completeness, boundedness, conversions of sequences are the same or are pretty much the same. In other words, um, metric spaces that are isometric uh, are essentially the same metric space up to, well, mathematicians use the word relabeling. So it's like if you have a metric space X and a metric space Y, and I say that these two guys are isometric, then that means that they are from the point of view of a metric space, X and Y is essentially the same. They have the same properties from the point of view of metric space, so the metric space properties. So that just means that the points in X are just being relabeled as the points in Y. So what do I mean by relabeling? You could think of it like this. For example, if you're learning, let's say you speak English and you want to learn, let's say French, you know that there are these um, translation dictionaries where half of the dictionary gives words from English to French, and then the other half gives words or sentences from French to English. So it's a dictionary that allows you to go back and forth between two languages. So that's the same thing here. That's what we mean by they're the same up to relabeling. Um, so what is the dictionary in this case that allows us to go back and forth between these two metric spaces? It's this function. It's this bijective isometry. This is essentially the dictionary that allow us to go back and forth to convert between these two metric spaces. Okay. So what we're going to show in this result is that we're going to show which properties hold or transfer over when these metric spaces are isometric. Okay, and again, an isometric metric space is just a metric space with a bijective isometry connecting it. So the first thing we want to show is that if F is a bijective isometry, then its inverse, of course, the inverse goes the opposite way, it's going from Y to X, is also a bijective isometry. Okay, so let's see how to do this. So since f is a bijective function, you know that f inverse is also a bijective function. So maybe we can start by writing that. So suppose, let's say, f from x to y is a bijective isometry, then f inverse is also bijective. Okay, because remember a function is bijective. Maybe I should write that. Recall a function f from x to y is bijective if and only if it has an inverse. So if and only if there exists an inverse. That is, if there exists another function, let's call him g, from y to x, such that g of y equals x whenever uh, f of x equal y. In other words, g undoes what f does. So f takes x to y. What does g do? G takes y to x. So g just goes backwards. Here we call g as simply f inverse, right? So this function g is what we write as the inverse, just to emphasize that it is the inverse. So a function is bijective if it has this inverse that exists. Okay, so if f is bijective, then f inverse is also bijective. Why is f inverse also bijective? Because what is the inverse of f inverse? It's f. Then f inverse is also bijective. So I'll put here since it has, so maybe I should be more explicit than it, since f inverse has an inverse, which is f, right? The function f undoes f inverse, just like the function f inverse undoes whatever f does. Okay, so that's something you probably knew from undergrad. If f is bijective, then the inverse is bijective. What we want to do now, or the real part, is to show that the inverse is also an isometry. Okay, so to show something is an isometry, I just need to verify that it preserves the distances with respect to the metric. So to show f inverse is an isometry, isometry, we need to show that uh, for any 2 points. So now remember, f inverse goes from y to x. So I need to take any 2 points in the domain of f inverse. So any 2 points, y and y prime, belonging to the domain of f inverse. So these guys belong to y. So for any 2 points in y, we have that the distance in y between these 2 points, right, is equal to the distance in x of the image of these 2 points, right? So this is what we want to show. Required to show. Yeah, that's what I want to show. Okay, and let's have a diagram when you're doing this for the first time, just to keep track of where everything is. Okay, so here's x and here's y, and f is going this way, right? So f is a bijective isometry, and f inverse is going the opposite way. Right? So f inverse is going this way. So if I want to show f inverse, right, is an isometry, then I need to take 2 points in the domain of f inverse. The domain of f inverse, you see from the picture, is equal to y. So I take these 2 points, y and y prime, and I look at their image. So their image under f inverse are these 2 points, f inverse y, and this guy here is f inverse y prime, right? And I want to show that the corresponding distances remain the same. Okay, so how to do that? Very simple. The hard part of these proofs is to just keep, this is just sort of keep track of where these points are, because sometimes, because you see, we're going to be jumping back and forth between the metric space X and Y. I'm going to be moving back and forth. So you just need to keep track of which metric space you're in. So what I could do is let's just say let Y and Y prime belong to this guy here, Y. Now, since F is bijective, right? So since F is a bijective function, bijective means one-to-one and onto. So Y and Y prime are in the codomain of F. So since F is surjective, that means that there are elements in X which map onto it. So since F is a bijective function, there exist two elements, X and X prime in X, such that F of X equals Y and F of X prime equals Y prime. Okay, I'm using the idea of it being surjective there, because if a function is surjective and I take two elements in the codomain, that means there exist two elements in the domain which map onto it. That's what surjective means. Okay, everything in the codomain gets hit by something in the domain. And since F is bijective, so you can't always do what I'm about to write, but you could do it if the function is bijective. If the function is bijective, you can move F across. So this implies that X equal F inverse Y and X prime equal F inverse Y prime. You could only do this if your function is bijective, okay? So now we could consider, right? I just need to consider. So let me scroll back up. What do I want to prove? I want to prove this part here. Okay, so let me just take, you can start at any side. So maybe let's start with dx, F inverse Y, F inverse Y prime. Okay, so consider d sub x of F inverse Y, F inverse Y prime. Okay, what I'm going to show now is this. But I'm starting with the right-hand side. Okay, I'm starting with the right-hand side and I'll show the left-hand side. Okay, so consider the right-hand side is this guy. Now from above, F inverse Y is X, right? And F inverse Y prime is X prime, okay? Now F is an isometry, so that means that this distance, right? F is an isometry is the same as this distance, the same as the distance between the image. Okay, so since F is an isometry. Okay, usually if you see these proofs in textbooks, they do it in one line because it really is a one-line proof. But I'm just unpacking it so that you know, so that it's a bit more clear what's going on at each step. But once you know what is going on at each step, you could write the one-line proof. Okay, but it's just looking like a long proof because, for example, I'm drawing a picture, I'm writing down explicitly what I'm required to prove. I'm staying at the beginning here. I'm redefining or recalling what is a bijective function. So when you're writing the actual proof, you don't have to do all of that. Right? You could just write this lines that I'm about to write. Okay, so since F is an isometry, we have this thing. And F of X is Y and F of X prime is Y prime. dy, F of X is Y and F of X prime is Y prime. Okay, so that's it. You're done. That's what we wanted to show, right? In this green box. That's what we have in this green box. So that's the proof right there. Yeah, so therefore, F inverse is an isometry. That first part is done. Okay. The second part is F inverse is a homeomorphism. So remember what a homeomorphism was? Let's recall again what is a homeomorphism. F between two topological spaces or metric spaces is a homeomorphism if, so you have a few things. F is bijective. The second thing is F is continuous. And so notice this distinction. If I scroll all the way back up here, when we were looking at properties of an isometry, we showed that if a function is an isometry, oh sorry, this one. Yeah, I went too far, too far back. Yeah, so we showed that if a function is a bijective isometry, then what we just showed is that the inverse is automatically also an isometry. You don't get the same thing for homeomorphisms. Okay, what I mean is that if f is a bijective continuous function, there's no guarantee the inverse will also be continuous. The inverse exists because it's bijective. Okay, the inverse exists, but there's no guarantee the inverse will be also continuous. That's why we need to add in as a third condition that the inverse is continuous. Okay, so that's just something to note. For the isometry, no need to add in that the inverse, oh sorry, if the isometry is bijective, right? No need to add in that the inverse is also an isometry because you get that for free. That is always true. Okay, so that's what a homeomorphism is, and what we want to show is that if you have a bijective isometry, then it's a homeomorphism. So we actually already prove all the results to do this. So we just need to piece everything together. So the proof is, suppose f from x to y is a bijective isometry, right? So I want to show it's a homeomorphism. So we just need to check off these three conditions, but we already proved everything to check off these three conditions, right? So suppose f is a bijective isometry, then obviously f is bijective, right? It's bijective. So condition one, check. Is f continuous? Now remember we proved that if we have an isometry, then that isometry is not only continuous, it's uniformly continuous. Okay, so yes, it is also continuous. Okay, so we already proved that. So since every isometry is uniformly continuous, right? That's what we proved. F is continuous. Right? Condition two, check. And now is condition three also true? Is F inverse continuous? Now, what do we just prove in the first part? We show that if F is a bijective isometry, the inverse is also an isometry. Okay. So, so we say by part one, F inverse is also an isometry. Right? But all isometries are continuous. So F inverse is continuous, So by part one, F inverse is also an isometry. So F inverse is also continuous. All isometries are continuous. Okay? Now you get the third one, right? So F is a homeomorphism. Therefore, F is a homeomorphism. Okay, so we just piece together everything that we had from before. Okay, so the second part, check. Now the third part, we're going to essentially use the third part to prove. So I know it looks like a lot, but we're going to use this third part, and then from this third part, each of these are going to follow. Okay, so the only main part here is this third one. And that is saying that if A is a bounded set in X, if and only if its image is bounded in Y, is a bounded set in Y. So in other words, the bijective isometry takes bounded sets to bounded sets. So it takes bounded sets in X to bounded sets in Y, and it takes bounded sets in Y back to bounded sets in X. So it preserves the bounded sets. Let's see, I'll do that one. True. So again, let me just recall what it means for a set to be bounded. So a set E, let me not go X, let me just say a set is bounded. Yeah. A set, maybe, okay, let's use A. A is bounded if it has a finite diameter. Right? So remember what the diameter is. So sometimes we put D of A, or sometimes it's written as DIAM of A, however you want to write it. So the diameter of a set, it's just the, what we're going to do is we're going to look at the set of all possible distances between points in that set. So I want to avoid writing X and Y because we're going to use that later on. So I want to make this general. So distances, let's use A and B. Okay, so you take all the distances between A and B, where A and B belong to this set. So measure all the distances between all points, and then you take the largest that would be, or the supremum. And this has to be finite. All right, so now we say suppose A, which is in X, is a bounded set. So it's a if and only if. So maybe I should have said we're going this direction, through this direction. Okay. So suppose A, which is subset of X, is a bounded set in X. I want to show its image, f of A, is also bounded. Okay. So all I have to do now is write down what is the diameter of f of A, right? Then the diameter, so the diameter of A is finite, right? But the diameter, I want to know what is the diameter of this set, f of A. So by definition, that is the supremum over all distances So let's go y and y prime such that y and y prime belong to this set f of a. Okay, and now I have to be specific because we have two metric spaces. So this is the distance in y, and this is the distance in y. Okay, so it's a distance between any 2 points in y where those 2 points come from the set f of a. Right? That's just a definition of what the diameter of a set is. Now I know that f is a bijective isometry. Okay, f is a bijective isometry, which means that for these 2 points, y and y prime, remember f is bijective, so y must have been equal to f of x for some x, and y prime must have been equal to f of x prime for some x prime, where x and x prime belong to a, right? What is the set f of a? The set f of a is simply all function values where it comes from a. Uh, maybe I should draw a photo, picture to show this. Yeah, right. So it's always good to draw a picture whenever you can. Of course, the picture is in the proof. Okay, the picture is not the proof in analysis, but the picture helps us to figure out exactly what is going on. And from the picture, we could use it then to construct the proof. XY is F. And so this is the set A, right? It's bounded. And this is the image, F of A. Okay, so what I was basically writing there was I took any 2 points. Okay, here is y and here's y prime, right? Now, since f is a bijective function, what I was saying there was that this y came from this x, and this y prime came from this x prime. Okay, again, this only happens because f is bijective. Maybe I should emphasize that. F, which is bijective, and isometry. Right. Yeah, so that's what I was saying. So that's how I went from this line into this line. So I'm saying that that y was equal to f of x, this y prime was equal to f of x prime, and the x and the x prime came from a. Okay, so the picture now makes it a lot nicer. But f is an isometry. Okay, so this distance in y is the same as the distance in x of x and x prime. Okay, remember f is an isometry, so by definition, these two guys are equal, where x and x prime belong to a. So I could say sin f is bijective. That's what I was using to go from that line to this line. And this guy I was using sin f is an isometry. Yes. Oh, right there. Right. So METR. Yeah. Yeah. So once you have, so that's the picture that's the picture I had in my head. So that's the picture you should have in your head when you're doing these things. Okay. And what do I know? Well, this here, this last set, that's just the diameter of A, right? This is nothing but the diameter of the set A. It's the supremum over all distances of points where those points belong to A. That's the diameter of A. But A is bounded. So this guy is finite. Um, So that guy is finite. Uh, what so if A is bounded, then the diameter of f of A is bounded. Now, remember this was an if and only if statement. You can actually go backwards since A is bounded, right? What I'm saying is that you can actually go in reverse. You could say since or suppose f of A is bounded. So what if we suppose instead that this guy was bounded? Okay, then this guy is equal to the diameter of f of A, right? So essentially what we showed there, well, what do I want to write? Um, okay, here's how we're going to do it. We're going to do both if and only if at the same time. No need to rewrite this whole. Yeah, because what we just went through here holds regardless of whether A or f of A is bounded. This holds because we have a bijective isometry. Okay, so that's what I want to write. Suppose f from x to y is a bijective isometry. Then, right? So everything here, then the diameter of f of A equals the diameter of A. The diameter of f of A equals the diameter of A, right? Because look at what I was well, what we apply in each step. In the first step, we apply f is bijective. In the second step to the third step, we apply f is an isometry. So what we just showed there is that the diameter of the sets are preserved. So the diameter of f of A is equal to the diameter of A. Therefore, it follows that the diameter of f of A is finite, right? If and only if the diameter of A is finite, because they're the same number. They are equal to each other. In other words, f of A is bounded. That's what the diameter of f of A is finite means. F of A is bounded if and only if A is bounded. Right, cool. Yeah, so we didn't have to do a converse. We did everything in one go. Okay. So that's that one. So this guy, check. Now the rest of them is going to follow in pretty much the same way, and also just by definition. So the fourth one is saying Xn is a bounded sequence in X if and only if the image of the sequence is a bounded sequence in Y. So this follows straight from tree, because what is it? What is a bounded sequence? A sequence is bounded if the range of it is a bounded set. Let's just write one line for that. That was 4. Okay, so recall, what does it mean for a sequence to be bounded? Of course, there's a next way to write it. But let me write the definition. Um, a sequence uh, xn is bounded if the range or its range, so the range of the sequence is a bounded set. Okay, in other words, um, uh, that is, so usually you would see it written like what I'm about to write. So in other words, there exists some positive number m such that the modulus of xn uh, is, so now we count the modulus. Uh, okay, yeah, so you see, so this only makes sense if the sequence is real or complex valued. Otherwise, we have to put a norm here. So that's why usually we don't write this one. That only follows if you have like a norm on the space. Of course, if you have a metric, you could put then you can get a norm. It's just the distance from the point to zero. Uh, but then the space has to be a vector space, which is always true. Okay, anyway, we this is the definition we're going to use. So a sequence is bounded if the range of it is a bounded set. The range of it is just the set of all possible points, distinct points. It could be. Um so so let's see. Um the sequence xn is bounded, right? If and only if the range, so this is the proof of it. If and only if the range is bounded or is a bounded set, right? That's from definition. But what do we just prove? We just proved that if we have a bijective isometry, then bounded sets gets mapped to bounded sets. So that's the same thing as saying that the range of this new sequence, the sequence where the points are f of xn, is a bounded set, right? Because f is a bijective isometry. If f is a bijective isometry, then um, then it takes bounded sets to bounded sets. Okay, so if the range of this guy is bounded, then the range of this one is bounded. Yeah. This guy's a bounded set, which is the same thing as saying that the sequence f of xn is a bounded sequence. So it's bounded. Okay. So this is since bijectives and isometry takes bounded sets to bounded sets. Okay. So the range of this thing is a bounded set. So the range of something is a set, right? The range of the sequence is a set. And I'm saying that this set is bounded, right? But if you now take this set, I claim that these two sets are the same. Which okay, let's write it up. Right? That may have been a little gap there. So note these two sets, the range of this guy, sorry, um, f of the range of this guy. F of the range of this guy is equal to the range of f of xn, right? So lots of brackets. Okay, maybe maybe I can make it look simpler, right? How to make it look simpler? Okay, let's do it this way. Let's do it this way. Let E, okay, let the set E equal to the range of the sequence, okay? And again, that is just equal to the set of all xn, where n is a natural number. Okay, it's just a set of all possible values that the sequence could take for all possible points. So why is this different from the original sequence? Because, for example, the original sequence could have repeated points. What do I mean by that? Let's say I have this sequence, 1, -1, 1, -1, and so on. So in this case, it's a sequence of numbers, but it doesn't have to be a sequence of numbers, by the way, because it could be, remember, functions are metric spaces and so on. So it doesn't have to be numbers, but we'll do an example like this. So the range of the sequence E is, it will not be 1 -1, 1 -1, and so on. It's just 1 and -1. Okay, it's just all possible distinct values the sequence could take. Okay. So let E be the range of the sequence. I claim that f of E is equal to, so now I need a next E, yeah, let's do E prime, maybe. What's the next letter? E, F, I don't want to use F. Okay, I don't want to use E prime. You may think that's a derived set. Let's use G. Okay, so G is the range of this sequence. What I do is I apply F to every point in the original sequence, Xn, right? So the range of this new sequence. So this is just the set of all distinct points, f of xn, okay, where again, n is a natural, not x. Okay, okay, now I can write it. I claim that f of E is equal to G. That's what I was trying to say, right? So I'll leave this for you to try to prove. It's very easy if you just, sit and think about it, because if you take any element in here, f of E, right? Then what that looks like is, well, it's f of a point in the sequence, f of a term in the sequence. So any element in here will look like f of x, let's say k, for some k in the sequence. Okay. And clearly this will be in G, because G is the range of these things. And if you take any guy in G, then G is the range of points f of xn. So again, this will look like f of xl. But that's just f of a guy in the sequence. So that's this set. Okay, so it's just something you just have to sort of think about it. Yeah, so that's why essentially I did all that to explain why it is I could replace this line by this line. Okay. Um, range. This here is a bounded set, which means that f, so what I was doing there, I was taking f of this set. F of this set is a bounded set, which is equal to this set, is a bounded set. Okay, so if you have bijective isometry, it takes bounded sequences to bounded sequences. Okay, so what's the next one? Okay, so we have this one. The next one is if xn is a convergent sequence in X, if and only if this new sequence is convergent in Y. Okay, so 5. The property of convergent sequences. So recall, what does it mean for a sequence to be convergent? So a sequence xn is convergent or said to be convergent to a point x in x. So this is of course a sequence in x. A sequence in x is that it's convergent to a point in x if for any given any epsilon bigger than 0, there exists a natural number n such that for let's do capital N, there exists a big N, big natural number such that for any other natural number bigger than this guy, this implies that the distance between xn and x is less than epsilon. Okay. So proof now is I want to show that convergent sequences get mapped to convergent sequences. So suppose xn converges to x, right? And this is all taking place in the metric space x. Then for any epsilon bigger than 0, so I'm just rewriting the definition. Actually, this proof follows from the definition of convergence. Then for any epsilon bigger than 0, there exists a natural number n such that for any other natural number bigger than n, what do we have? The distance in x of xn to x is less than epsilon. So this is by definition of convergence. Right? But f is an isometry. Okay, f is an isometry. So this distance is the same as the distance in y of the images. Right? So this means that this distance, because these two guys are equal, right? F is an isometry means these two guys are equal. It's also less than epsilon, which means therefore the sequence f of xn converges to f of x, right? Because what did we do? This sequence converges to f of x because for any epsilon, I could find a natural number, such that for any other natural number bigger than it, I could find points f of xn, um, such that the distance between this distance in the y metric between this point and its so-called limit point is less than epsilon. Right? So that's the definition of convergence. In fact, you could go both ways in this proof as well. From here, since f is bijective and isometry. Okay, so this is actually both ways. This is actually both ways we did here. So no need to write the next way, but we proved the if and only if. You could go both directions in this. Right, so f takes convergent sequences to convergent sequences. Maybe let's let's actually write it out for the next part then, right? Because it isn't so clear why you could go backwards for some of it. Okay, so let's actually write it out. So let's actually do the converse part. Okay, so conversely, right? Conversely, suppose uh, suppose we have a convergent sequence. You could even name this guy yn convergent to y. Okay, but let's write it in this case. Conversely, suppose that the sequence f of xn converges to x, sorry, converges to f of x in y. F of x in y, right? Then for any, so same story, epsilon bigger than 0, there exists a natural number such that for any other natural number bigger than this capital N, this implies, so the convergence taking place in y, the distance between f of xn and f of x is less than epsilon, right? Now, since again, f is isometry, that means I could rewrite this as xn, x. Okay, since f is isometry, these two sides are equal. So again, therefore, the sequence xn converges to x. Yeah. So f takes convergent sequences to convergent sequences. Like I said, you could even you could call this guy, like you could call this, for example, yn, and you could call this y. So actually, if you have any convergent sequence in y, you could pull it back to a convergent sequence in x, right? What do I mean by that? So for example, this is saying that if you take any convergent sequence in x, then you can move it forward into a convergent sequence in y. What I'm saying is that you could go the opposite way as well. If you take any convergent sequence in y, you could pull that back to a convergent sequence in X, and that's because F is a bijection. So X and Y could be interchanged. Okay, so you can move back and forth between convergent sequences. And for Cauchy sequences, it's the same thing as what we just proved here. You just apply the definition of Cauchy sequence. Yes, that's that one. Uh, right, so we just need to recall what's a Cauchy sequence. Recall a sequence xn is the Cauchy sequence in X if for any epsilon bigger than 0, there exists some natural number, capital N, such that for N and M, which are also natural numbers, and N and M are bigger than this guy, we have that the distance, of course, in X, between these 2 points is less than epsilon. Okay, so that's the definition of a Cauchy sequence. And you can see that all we have to do is the same trick that we did up here. So it's the same thing. You just, once you reach to the point where you write the distance between X, you just sub in the distance for Y because it's an isometry. Okay, so I'll put over here as the proof, same as part 5. Right, so it's the same proof that you're doing, except instead of d of x and x, you will have d of x xn xm. Okay, and it will be the same proof, right? And the final part in this, so you could also move Cauchy sequences back and forth between these 2 spaces, x and y, if they are isometric. And the last part is saying if X is a complete metric space, so X is a complete metric space if and only if Y is a complete metric space. So if X and Y are isometric and you know one of them is complete, then the other one will also be complete. And the proof of this follows from what we just did. So recall, what is a complete metric space? XD is a complete metric space if every Cauchy sequence in X converges in X. Okay, and I claim that we already did everything we need to prove this. So we just need to piece together everything, right? So this part here, essentially what all the other parts before was to prove this, was to lead up to prove this, that isometric metric spaces preserve completeness. Okay, so I want to prove both sides. So we could say, how should I write this so that we only have to write it once, because it's an if and only if statement. X is complete if and only if Y is complete. So we could say, suppose X dx is complete, right? Then Suppose x is complete. I'm going to take a Cauchy sequence in y. Um, or maybe I should go the opposite way. Let y be a Cauchy sequence. Let y be complete. And okay, we'll do it this way. Let y and be a Cauchy sequence in y, right? Then, since f is bijective, they exist at xn in x such that f of xn equal yn. So all I'm saying is that each of these terms, these y's in the Cauchy sequence, come from an element in x being mapped onto it, such that f of xn equal to y, right? For each. Yeah. Okay. So now plus this sequence. So the sequence yn is the same as this sequence. Therefore, xn is a Cauchy sequence in y. But what did we just prove? We just proved that if this is a Cauchy sequence in y, then xn is a Cauchy sequence in x. Remember, we just proved that we could move Cauchy sequences back and forth using f. So if f of xn is a Cauchy sequence in y, then the sequence xn is a Cauchy sequence in x. Now x is complete. Okay, so that means that this guy is convergent, is a convergent sequence in x since x is complete. Right? Since x is complete. Okay, but what do we know if we have a convergent sequence in x again? So now we're linking everything we proved. So maybe I should state that. So Cauchy sequence, which one was the Cauchy sequence? Cauchy was 5, right? So by 5, 5, 6, 6, by 6, right? Since x is complete, and now this guy is by 5. So since xn is a convergent sequence in x, f of xn, this sequence is a convergent sequence in y, right? Why is that? By 5. Because f takes convergent sequences to convergent sequences. And what was f of xn? F of xn was just yn. So yn is a convergent sequence in y. Okay, since f of xn equal yn, right? So that's the proof. Therefore, y is complete. So this implies y is complete. Okay, so if x is complete, y is complete. And if y is complete, x is complete. You could just apply the same result in a similar way. So I'll leave that part for you. So conversely is done. Very converse, not conversely. Converse is done. Converse direction is done in a similar way. Right. So if you have two isometric metric spaces, if one is complete, the other guy is complete.